Today on the Perception and Action podcast. To celebrate episode 300 of the podcast, I'm going to talk a bit about my personal research journey. How has my thinking evolved over time? How did I self-organize towards the self-organization approach to skill acquisition? So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception and Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. Yes, today officially marks episode 300 of the podcast. Before I dive into today's topic, I wanted to take this time to thank everyone for their continued support. Through listening, telling others about it, feedback, using it as part of their classes, and especially those that have gone the extra mile and supported the podcast through Patreon. All your efforts keep putting gas in my tank and keep me going, and I definitely have no plans to stop. So, as I mentioned in today's episode, I want to do something a bit different and talk about my personal journey. I want to do this for a few reasons. Obviously, if you are a regular listener, I'm sure you have realized I'm a strong supporter of the self-organization / ecological psychology / dynamical systems approach to motor control and skill acquisition. But I wasn't always that way. I didn't immediately jump on the bandwagon. As you will hopefully see, over the bulk of my now 25-year research career, I've spent a lot of time thinking about and testing ideas from both the ecological and more traditional information processing viewpoints. For example, I've worked on topics including predictive control, cognitive models, representations, and automaticity. Heck, the very name of my podcast violates the central assumption of the ecological approach. It's perception action, not perception and action. My views about skill acquisition have evolved over time. So in telling you about how I got to where I am now, I hope I can get you to think about your own personal views. If you're skeptical about approaches like self-organization and ecological dynamics, maybe you share some of the same questions and concerns that I did. Maybe the answers that I found to this will help change your mind too, or not. If you are a strong, staunch supporter of the ecological approach, maybe my story will get you to think a little more critically about some of the ideas within these theories. I think this is essential for this area to continue to grow and develop. But either way, here it is. I was born... Kidding. This is not meant to be my autobiography. I'm going to try to stay on topic here. Although I was always fascinated by how athletes, including myself, did what they did, I really never for a second thought I could make a career out of trying to understand it. That all changed for me when I took a course in my second year as an undergraduate at Queen's University. The course was Sensation and Perception. S&P was team taught by a few instructors, but one of them completely changed my path. Barry Frost, who sadly passed away a couple years ago. As I talked about way back in episode 16, Barry had such a passion, knowledge, and excitement for what he did, you couldn't help but want to follow him. Although he did a few different things, Barry's main interest was the perceptual abilities of animals. For example, why pigeons bob their head when they walk. It's to stabilize their gaze. And how birds and butterflies manage to navigate over such long distances. He found they don't have internal maps, but instead couple their movements to information, in particular the plane of polarization of light. In addition to the main message that you can have a lot of fun doing research, I took things from Barry that would end up being puzzle pieces in my bigger story. First, when it comes to perceiving the world around us and controlling our actions, there's nothing really all that special about human beings. If you take the goals and needs into account, other animals have abilities that are equally, if not more, incredible and perfectly suited to their environment. The second thing I learned from Barry is a message that I would forget for part of my career, that you always need to consider the ecology or environment a performer has to act in. Like all animals, we are adaptive creatures. You can only make sense of behavior by considering the external forces that help to shape them. However, Barry also planted in me an initial seed of skepticism about ecological psychology. He was very interested in and did some of his major work in neuroscience. For example, he was one of the first to identify neurons that seemed to be detecting tau and time to collision, and he did a lot of work on the processing of optic flow in the brain. One of his favorite stories to tell was the time that he met James Gibson. He was super excited to talk to him about some of the neuroscience work and pose some challenges to him about the brain's role in perception. But apparently, upon hearing his comments, Gibson turned off his hearing aid and walked away. So this de-emphasis, almost dismissal of neuroscience and the amazing things the brain was doing, which like many students I was initially super excited about, planted a little bit of a red flag about the ecological approach for me. I will return to this specific issue in a bit. In the other course I was taking at the same time, Learning and Motivation, we spent several weeks going into the details of Skinner and behaviorism. Behaviorism is the idea that behavior can be explained purely by understanding stimulus-response relationships. You know, the famous salivating dog and the bell, without the need to take into account internal processing and feelings. This idea was, of course, largely dismissed in the 1950s and 60s in the so-called cognitive revolution in psychology. Over the years, the ecological approach to perception action has been frequently accused of being a type of behaviorism. Stimulus-response pairings have been replaced with information movement couplings, with both approaches having a similar dismissal of the role of internal processing. I really initially enjoyed learning about behaviorism. Being a person that likes math and was taking economics at the same time, I really liked the rigor of Skinner's approach and the attempt to describe the behavior in terms of formal laws. But I remember the exact moment I got disillusioned by it. We were learning about different types of reinforcement schedules and testing them in experiments with mice. For these, you would write out a little expression with R's for the reinforcers. In one experiment where the reinforcement food was unreliable and inconsistent, the textbook designated this as R sub F. After a bit of digging, I realized that the F stood for frustration. In other words, a cognitive concept was being hidden in the stimulus-response rule. In finishing up my undergrad career, there were also a couple other things that kind of steered me away from ecological psychology. First, like many people, I was initially fascinated by perceptual illusions and trying to understand what they told us about perception. The ecological view, of course, essentially reduces illusions to fun but trivial tricks that are the result of highly contrived and restricted viewing conditions. The other concept I was really interested in at the time was perceptual constancy. How we could see things as having the same size, color, brightness, etc., despite massive changes in the viewing conditions, being in sunlight or shade or close versus far away, for example. From what I learned at the time, I couldn't imagine how this could happen in any other way than some compensation process going on inside our brain. Little did I know, Gibson would give me a different answer in the form of invariance. So when I started looking around for where to go to grad school, I really was a believer in indirect perception. That is that the brain was doing a lot of work to help us process cues and interpret information that was out there for us to act. My exposure to ecological psychology was really just a few mentions here and there in my classes, and I was not really compelled to dig much deeper at the time. What I did know was that 1, I wanted to keep studying the fascinating topic of perception, and 2, I wanted to work on applied topics, not just basic questions using artificial lab tasks. Although studying perception for perception's sake was somewhat interesting for me, I really wanted to understand how we did things out there in the real world. This was motivated by a couple factors. First, I was still playing hockey as a goaltender at the time and was fascinated by how people that weren't really physically gifted, like me, seemed to be quite successful at sporting skills. Second, there was something that had bothered me for a long time I wanted to try to do something about: driving accidents. As I think I mentioned on the podcast before, I went to high school in a rural area in Ontario for 5 years, as we do in Canada. Every single year I was there, a student was killed or seriously injured in a driving accident. How could something we created ourselves to make our lives better be so harmful? There must be a way to understand why people are having accidents and help address this problem somehow. That's when I discovered Martin Regan at York University. Martin, who I talked about a bit back in episode 18, had really everything I was looking for at the time. He worked in perception, applying it to areas like sports, aviation, and driving, and he was in Toronto. So it meant I could go back closer to where I grew up and where most of my friends still were. Working with Martin was really interesting because he didn't really associate with one or the other psychological theories or camps. He wasn't even a psychologist at all. He was a physicist. In our lab, we had to assemble and build a lot of electronic equipment: amplifiers, attenuators, gates, A to D converters, and so on. We use these to generate visual stimuli for our experiments. If you saw the wall of electronics, literally, I used to create a simulated approaching ball at the time, you would laugh now. And this was really how Martin conceptualized perception as working: a series of neural units in our brain that were modifying and altering the incoming signal from our eyes to create detectors for particular types of information. So for example, we take a unit, a neuron, that was sensitive to an edge that moved left, and combine it with one that responds to movement to the right, plus one that likes movement up, plus one that likes movement down, and voila, you have a looming detector. Then we might have to add a filtering stage to reflect our relative sensitivity to different rates of looming, and so on. If you look at the models of visual perception Martin developed in his papers, what you will see are essentially circuit diagrams, very similar to the ones you might get in a manual that comes with your TV. So definitely not really an ecological approach to perception. But for me at the time, I really appreciated the rigor of it, and the fact that compared to some alternatives, which use very vague terms like mental models with just boxes and arrows, for what was going on in the brain, Martin was trying to figure out exactly what these processes were. The experimental approach we used in Martin's lab was psychophysics. So we took painstaking efforts to control and systematically vary the visual stimulus presented to the participant, the physical, and measured their responses to it, the psychological. Responses in almost all of our experiments came through a button box you held in your hand and were asked to make a choice. Press the left button if the object on the left is moving faster, and the right button if the one on the right is moving faster. The logic of how you can apply this approach to real-world skills like in sports and driving is that if you can identify which aspects of the visual stimulus you are more or less sensitive to, and which aspects you seem to base your judgments on, then I should be able to predict and or explain conditions in the real world that will give a performer problems, and or might require them to learn to use something else. So for example, in my PhD dissertation work, I looked at how we judge the time to collision of an approaching object. We identified some situations in which looming and tau information is relatively ineffective. For example, when the object is really small or it's non-spherical and rotating. Then we measured how accurately people could judge time to collision in these situations, and sure enough, when they just had tau, they made errors. It was only through adding binocular information about the object's movement that they made accurate judgments. And this does have some real-world consequences. The issue of the object's size has been used to explain accidents on the road involving child pedestrians, and the rotation issue can explain why it's difficult to catch a rugby ball or a football not thrown in a perfect spiral. Check out the blog post I linked in the show notes where I talk about this in detail if you're interested. So in psychophysics, we're looking for these situations where your ability to use certain types of information in the visual stimulus are relatively poor, and try to identify what you use and when. After having completed this work and moving on to doing a postdoc, I was very proud of it and really appreciated the skills I learned from Martin in terms of analyzing a visual stimulus and designing well-controlled experiments. However, there were some things that left me dissatisfied about what I was doing. First, as I said, in psychophysics, you try to identify the visual information that a performer could use for a particular task, then test whether or not they're sensitive to it. For example, as I discussed back in episode 25b, an object's acceleration rate has been suggested as a possible information source we could use in some situations, for example when catching a fly ball. But experiments have shown that we're pretty terrible at judging acceleration, so people must be doing something else. But there are a couple problems with doing things this way. First, with the rare exception of things like acceleration and fairly esoteric conditions I studied in my dissertation, the answer to the question, is an observer sensitive to that visual information source, is almost always yes. So it doesn't really help you narrow down the possible solutions very much. Second, as I've talked about on the podcast a few times now, for example when looking at the dorsal versus ventral streams, just because we can't use some type of visual information to make an explicit judgment, for example when deciding whether to press the left button for accelerating and the right button for decelerating, this doesn't mean that we can't use the same information to regulate our actions, because we now know that these two things are actually using different brain areas. The other issue I had, of course, was that all the work I've been doing so far was uncoupled. I spent hours and hours carefully manipulating the visual information just so people could quote-unquote act on it by pressing a button. During my PhD, I also started to read a bit more about Gibson's work. In particular, the gateway drug for me was the book Direct Perception by Michaels and Carrillo. The main initial message that resonated with me from Gibson was that you could only understand perception and action by studying them together. This message both brought back the idea of preserving an animal's ecology, I learned from Barry Frost, and explained some of the shortcomings of the approach I was using. By just focusing on the perceptual side of things, all I was really asking was whether or not a performer could use this visual information source. What I really wanted to know was, did they actually use it, and if so, how? So I decided I needed to keep them coupled and think more about the motor control side of the equation. So for my postdoc, I was looking for some way in which I could combine the rigorous control over the visual stimuli I had used in my PhD with more realistic responses and actions. Although I found a lot of the field work that people like David Lee did interesting, there was just not enough control there for me. The answer for me was virtual reality. At the time, I was lucky enough to get offered a position at Cambridge Basic Research, a lab in Boston that Nissan had created for studying driving. Bingo! It had a VR system, a fancy driving simulator running off Silicon Graphics computers, and it also gave me the opportunity to tackle the burning issue I talked about a few moments ago, trying to reduce the number of driving accidents. When I first got there, I tried to take advantage of the driving simulator to figure out how drivers were using different sources of information to control their behaviors. For example, I did a couple studies where we looked at the information used to make decisions and control the vehicle when overtaking and passing another car. From this idea, a warning system was developed. With Dario Salvucci, I worked to develop a somewhat popular model of how visual information is used to steer a car. Finally, I reconciled my thoughts about illusions, which I now would say are just perceptions consistent with the available information rather than misjudgments, by looking at one that occurs in driving. But the biggest career-changing moment for me actually came when I wasn't doing anything related to driving. In our lab, we had a few different motion trackers that we used to measure the head position of the participant in the simulator. I always wanted to use one of these systems because I was really excited about the possibility of being able to measure action in the same way I could measure perception. So whenever one of these systems wasn't being used, I would pull it aside and start secretly messing around with it. The first one I used was a Polhemus Fast Track, a magnetic wired system. After playing around with it for a few days, I was able to pull the data out of it into a simple program I wrote. At the same time, I was also playing around with coding computer graphics, using the standard at the time, OpenGL. I knew that I was not going to have access to all the fancy electronics we used to generate visual stimuli in Martin Regan's lab, so I needed another way. For that, I would take code that someone else had written and change and remove things to see what happened. Usually it just made it crash, but sometimes I would learn something. One such piece of code was for playing a 3D Pong game, where you moved a little paddle with the arrow keys on a keyboard to play virtual table tennis against the computer. After some messing around, I was able to combine these two things. So I could put the motion tracking sensor on my hand, and it would move the virtual paddle on the screen to play the game. Hallelujah! I had coupling. I could have a participant move in response to and interact with my visual stimuli, and I could measure it. I seriously think a little tear came to my eye at that moment. Over the next few days, I removed the table and the paddles, changed the type of ball, and mounted the sensor on the end of a bat. And voila, version 1.0 of my baseball batting virtual environment was born. I collected some data with my batting VR in Boston and then moved it to Arizona State when I got my first faculty position. In my first set of studies, I asked batters to try and hit the virtual ball in a really stripped-down environment. Just the ball, no field or no pitcher. I purposely decided that I was going to systematically add things as I went along to see how it changed performance. What I found in these first set of studies would again steer me away from ecological psychology for a few years. Even though it was theoretically possible for a batter to adjust their swing purely based on the visual information available from the ball, specifically its rate of expansion or tau, they didn't seem to do that. Instead, their movements were equally influenced by things like the sequence of pitches, whether they faced 3 fastballs in a row or 3 changeups, and the count, the number of balls and strikes. For me, this was clear evidence that the batters were using knowledge to predict what the pitch was going to be and to control their swing. So I spent the next few years trying to understand how this might be implemented. For example, in a paper I published in 2001, I developed what I call a model of cognitive processing in baseball batting, which was a Markov model of how batters combine information about pitch sequence and count to generate an expectation or prediction about the upcoming pitch. In a paper that would eventually get published in 2009, I used another internal type of model to explain how batters decide when and when not to swing. This involved an interaction between initiation and inhibition processes, again heavily based on the batter's prediction about what the pitch would be. During this time, I even directly challenged a central idea within ecological psychology, prospective control. In a study I published with my grad student Randy Seifert in 2005, we showed that when you don't constrain people to just move laterally, As had been done in many studies at the time, their catching behavior seemed to show signs of prediction, specifically reaching out to cut off the ball. So you can see I was firmly in the information processing and prediction camp at the time. In terms of skill acquisition, this is when I really first discovered Fitz and Posner's model, which I discussed back in episode 129. The ideas in this seem to be consistent with some of the things I was observing in both driving and baseball batting studies. Specifically, more experienced performers seem to be doing things more automatically. A big turning point in my career came when I read Sion Beilock's 2002 paper, in which she used dual tasks in golf putting to test some of Fitz and Posner's ideas. As reflected in the title, When Paying Attention Becomes Counterproductive, she found that when you drew an expert performer's attention towards skill execution, it hurt performance, while it actually helped novices. I really love this paper because it tested these ideas in a very rigorous and controlled manner. My interest in this work also reflected another main thought that was going on through my head at the time. Understanding the control of action was not going to come from focusing exclusively on the perception of information. I needed to turn to studying more quote-unquote cognitive processes like attention and memory. So in a 2004 paper, which is now my most cited piece of work, I basically ripped off Sion's study and replicated it with baseball batting. While I like to think I added a few interesting twists too. This would launch a series of studies in which I showed how important attention seemed to be in action control. When it was turned inwards towards skill execution, either artificially in an experimental dual task, or due to more natural causes like pressure, a streak in bad performance, or an injury, it really seemed to hurt expert performance in a manner highly consistent with Fitz and Posner's ideas related to automaticity. So about 10 years ago, I was really a long way from where I am now in terms of my approach to understanding perception action. How in the world did I get here from there? Well, consistent with where I would end up, it's been a very non-linear process, with the influences and events I'm going to describe interacting over time instead of happening in any kind of order. One such influence came when I started to attend and present at ecological psychology conferences. I have to admit I wasn't really too impressed with the field in these first encounters. As you can imagine, when I presented my baseball batting work showing the role of prediction and anticipation of the upcoming pitch, it wasn't exactly met with huge fanfare by the ecological crowd. After one of my presentations, I will always remember that Michael Turvey stood up and announced to the room that basically, this work was interesting, but the task was way too complex to understand. This ticked me off a little bit, to be honest, and also was very consistent with a lot of what I was seeing and disliked about research in this area. A lot of it seemed to be using very artificial tasks, like swinging pendulums back and forth. While I now know that these were chosen because the task dynamics could be modeled more easily, I thought this was the field that was supposed to be studying actions like the things Gibson talked about, landing planes and driving cars. Also, at the time, a lot of the questions I got after my presentations were something like, couldn't you just describe expecting a fastball or a curveball as being in different attractor states? At the time, not having really dug into dynamical systems very much, such comments just sounded like a difference in semantics to me. I didn't really see how switching to talking about attractors instead of predictions and expectations would help me understand hitting very much. So as you can hopefully see, I didn't just jump on the ecological bandwagon. I used to say at the time, I feel like I'm doing ecological psychology in my work until I go to their meetings. My interaction with the researchers in the ecological psychology area changed a lot from these first slightly negative interactions when I was able to take more time and really talk to people. In particular, discussions with Reinoud Bootsma were really in the terminology of dynamical systems, bifurcation point in my thinking. Or put another way, my approach to understanding perception action started to lose some of its stability, and I was encouraged to explore. If you have never met Reinoud, he loves to get into heated debates about perception action, and he has an incredible knack of getting right to the core of things and challenging you. As I mentioned a few moments ago, one of the things that I didn't really like initially about the ecological approach was that it seemed to largely dismiss neuroscience and all the amazing things our brain was doing. I will forever remember Reinoud's comment when I asked him about this at a conference. Quote, "I study catching, so cutting off my hand would affect my performance just as much as cutting off my head." As I now know, and Reinoud was trying to illustrate, it's not that brain activity in neuroscience is dismissed completely in the ecological approach. It's just not as magical and important as others think it to be in other approaches. It's just another level of analysis in a complex system, no more or less important than EMG activities in muscles, kinematics from motion tracking, etc. Another thing Reinhard really challenged me about were the problems or errors I'd been identifying with perception. We can't perceive tau when the object's too small or the ball's moving too fast, an object is rotating, etc. As he pointed out, if we really did have all of these limitations, wouldn't we be having accidents and failing all the time? Without coming out and saying it, he was telling me that I was measuring and thinking about perception in the wrong way. I needed to keep them coupled to allow calibration to occur. And indeed, I saw this in a lot of my studies that followed. I also owe a lot to discussions I had with Bill Warren, Brett Fagan, and Gilles Montin. As I know many people listening have likely experienced, the concepts of dynamical systems can be very difficult to understand and quite impenetrable at times. These three were exceptional at bringing the ideas down to a level I could understand, whether it was talking about attractors with Bill and Brett or perspective control with Gilles. So in a nutshell, I started to get much more interested in trying to understand these ideas in this approach on a deeper level. Another point of instability in my approach came when I started to get more serious about applying my work in the field, in particular, working directly with baseball players and coaches. I began to realize something that I strongly believe now. When you take a perception action problem and try to solve it by appealing to some internal model or representation, like I was doing in my predictive models of batting, it doesn't really get you very far. It seems like you've done a lot, but all you've really done is shifted the problem around a bit. For example, in my model, I could describe how a batter takes the knowledge of the situation, the count, and combines it with the history of events and the information early in the action to generate a prediction about what's going to happen. But what do they actually do with that prediction? Say a batter predicts the next pitch is a fastball. How does that give rise to a swing? Do they just use a ballistic pre-programmed swing that gets the bat to a certain place in time? My data didn't seem to show that. Similarly, if an outfielder is using an internal model to predict where on the field a fly ball will land and when it will get there, what exactly do they do with that information? Do they execute a headlong sprint to that location? Or do they somehow modulate their running speed based on the predicted time of arrival? The point I'm trying to make here is that resorting to solving the perception problem with an internal model or representation just leaves you with a huge motor control problem still to solve. How is the information coming out of the internal model actually used? Who or what is looking at its output? And we see this a lot in the information processing models. Frequently in diagrams illustrating the model, there will be a little box that says execute action without actually saying anything about how this is done. Contrast this with prospective control models used in ecological psychology. In these models, the problems of perception and action are solved at the same time. For example, when running to catch a fly ball, prospective control models explain both what information is used and how it is used. The fielder runs to maintain a relationship between the information and their movement. If this relationship starts to be broken, it tells them whether to speed up or slow down. By the way, if you're interested in this specific issue, please check out the Journal Club on Prospective Control in episode 194. But the bottom line for me is that if you want to get really serious about the issue of how we use perceptual information to control our actions, especially for the complex ones used in sports, I think you will see that there are major limitations with the information processing internal model approach in this regard. Another major turning point came a few years ago when I really dove into the work of Nikolai Bernstein. I had heard his name before and understood the basic concept of the degrees of freedom problem, but it took me a while to get to one of his main messages. Skill is all about coordination. It's not just about the position of a body part at the start or the end of a movement. It's about how different body parts work together to form a movement solution. Like many researchers, I was overly focused on how movements started, in things like reaction times, and how they ended, in terms of performance outcomes, without appreciating all the magic that happens in between. A big shift in my thinking also came when I started to really appreciate individual differences in how this coordination occurs. This is something I've always struggled with throughout my career. I saw this happen all the time in my studies, but had spent most of my career suppressing them by calculating averages, throwing away outliers, and designing tasks that were deliberately designed to produce low variability by being very restrictive. Over the years, I've stood and watched literally hundreds of highly skilled baseball players participate in my studies, and I had always focused on what was the same between them. It took me a long time to shift my lens and realize that looking for what was different was equally, if not more important. More recently, as I began to read about, observe, and implement training methods like the CLA and differential learning, they have just worked better for me. It's funny, in my research design, I have always had a healthy skepticism about verbal instructions. So instead of just telling a person to judge the time to collision, not the distance of the object you see on the screen, or just telling them to focus on your elbow, not something else when swinging, I designed the experimental tasks so they had to do these things or they could not achieve the goal I laid out for them. This is why, for example, I use dual tasks, what I would now call a task constraint manipulation, in my attention experiments instead of just verbal instructions like most research in the field. While I'm not denying the power of words, to me it's just much more effective to influence a person's behavior by manipulating other task constraints more directly. A final point I will make here is that as I've gone later in my career, I've really enjoyed the challenge posed by using an ecological approach. Specifically, trying to solve the problems of perceptual-motor control without appealing to some internal model or mechanism, seeing how much behavior you can get for free, as Bill Warren once said. I'll talk more about this in a future episode, but when you do this, I think it makes you take a much harder look at the information available and the nuances of the movement. As I've taken a closer look at both the information and movement side of things in my research, I have found there are a lot of answers there. So that's where I'm at. I could tell you a lot more about how things have changed with my thinking in terms of things like how baseball batters use the count and pitch sequence and the effects of attention and pressure, but I will save that for future episodes so I can dive into them more deeply. If you've made it this far without stopping the episode, then I will say thanks again for listening. This is Rob Gray from ASU. Cheers for now, and keep 'em coupled.